Okay, thank you. Welcome. I'm Gabriel. I'm from a distributed Scala consulting based in South America, called Scalent. And I wanted to talk about like the reasonable or unreasonable effectiveness of mathematics for programming. All this is based on actual events, but some incidents or characters or timelines might have been changed for dramatic purpose, just a disclaimer. That means don't take everything as I say as true, maybe just double check that. But the idea for this talk is based on there's a kind of known paper that is the unreasonable effectiveness of mathematics for natural sciences. And Kant argues that many of the very useful things for physics especially came from mathematics, but they were first invented or discovered as abstract things, and then they find out like a real application. And when it starts with the example of pi, that really is the relationship between, I don't know, the diameter and the perimeter of a circle. But then you find pi in the, I don't know, the distribution, the Gaussian distribution, and you find pi in very weird places, and that really has to do with the circle. And then for me was the examples. What about programming? We have things that are kind of invented, discovered, that we use, we apply, and they're really useful. But when they were created, they have no idea what we're going to do with that. But let's start with the story. It was when the 20th century started, we had Whitehead and Russell write a big treatise trying to explain all the mathematics with formal logic. And they were like very hopeful. They were thinking that with logic they can explain the whole mathematics, and they have a firm foundation. And they were trying, and they formulate basically 3 claims. They wanted to have a formal logic that can explain, that has no contradictions, because obviously if you want to define theories, you don't want contradictions. They want their logic complete, that all mathematical statements can be proven that formalism. And they wanted all the statements to be decidible. Even as late as 1930, Hilbert believed that all the problems can be solved. But Kierkegaard had bad news for them. Basically, this guy, even like 2 days before that, Hilbert did claim that they can solve everything. This guy, 2 days before, had already proved that not. They created the incompleteness theorems. The first one was basically prove the first things they wanted, the Hilbert wanted, Gödel proved that it can be done. Any consistent formal system that contains is complex enough to contain arithmetic is incomplete. There are statements that cannot be proved or disproved. And now the second one, if you have a formalized system that contains elementary arithmetic, then the system is not consistent. Well, the only thing that left for Hilbert was the incisive problem that developed that every statement, that exists a method that you can decide for every statement that is true or not. We don't have good news for that anyway. The first proves that also is not possible came from Alonzo George with the lambda calculus. He created a formalist, basically created the lambda calculus to prove that the statement cannot be decidable. Gödel saw it. I didn't like it. He saw it was too complex. He tried to he also did his own proof with something called recursive functions. I think he didn't even publish anything. It just, I think it was in a conference with, in the same university with George. But then came also Turing that proved the same thing using logical computing machines that we know now as Turing machines. And actually, Turing went one more step, and it discusses philosophically what means like an algorithm and what an abstract machine following step by step will do to calculate the result. And that was more important because the chart has just the lambda calculus. It was kind of a presentation for that. But Turing had more, it went more into the philosophical side. So that's kind of a famous paper that creates the Turing machines. And really, Kierkegaard really liked that. That's what the thing is with Turing machines is like, because they were really formalized of what steps to do, it was easier to translate that into an actual machine. Before that, it was just, these guys were just imagining humans following step by step. But like, I don't know, 20 years later, they have like real machines doing that kind of stuff. So I think kind of the Turing machine, like a machine writing and reading in a tape, kind of dominate the kind of the paradigm and the way of thinking. But at this point, Turing machines are complicated, are hard to reason about, they're hard to compose, they don't work well in parallel. That's why the lambda calculus, because of functional programming, is getting more popular now. The whole idea of the lambda calculus is to have using substitution to calculate the result of an expression. We already have many presentations of lambda calculus that help me, so I don't need to spend a lot of time. But basically, it's very simple, very minimal. We have variables, we have abstraction, and we have application. And that's kind of the whole lambda calculus. In a little more formal terms, we have variables, abstraction of a variable with the term, and application of one term to another. And one of the most kind of important things, way of calculating with lambda calculus is the beta reduction that basically combines abstraction with application and means whatever an x appear in the first term, replace it with the second term. That's how you can go from one big lambda calculus formula to a final form. Here are some examples. I think yesterday were here, how you count with lambda calculus, how you sum, only using functions and application and abstraction, nothing else. No numbers, no symbols, whatever. You can create a logic also. This one is interesting. Lambda calculus has no recursion. And here you can create, it's a combinator that once you apply, if you reduce it, you get the same combinator with the function applied one time. Basically, you encode recursion with this. That's kind of things we can do, like with very basic things of the calculus. Sorry. But yeah, but I'll have all this to do with programming. George created lambda calculus to explain how the divisibility problem isn't possible to solve. But somehow we figure out that this is perfect for programming. I guess that's one of the things that is really amazing is probably if you go to church and say, oh, we are using lambda calculus to write programs, and say, You're not supposed to do that. That's famous because one of the first kind of, not totally based on lambda calculus, but really inspired on lambda calculus programming languages was Lisp. That is very minimal, has just a couple of, I think it has 11 just forms, they call it. The only difference is this Lisp, because to make it easier to implement, it has like dynamic scoping. And there's another kind of closer version that is Scheme, that is almost, I think, as close as you can get to lambda calculus in like a general programming language. And if you like Scheme, I totally recommend this book. It's a great way to learn Scheme. Even it gives you if you have to write the in combinator, it makes you prove that the divisibility problem. But then again, lambda calculus used for programming. But there's more things from mathematics. One of the ideas to get a good foundations for mathematics was to use, oh, sorry. One second, yeah. Was to use set theory to use as a foundation of mathematics. But set theory has this annoying property of leading to this kind of paradoxes. The famous Russell paradoxes. You have a library. You have libraries. Libraries has catalogs. Some libraries print catalogs. Some libraries don't include the catalog in the catalog itself. Some libraries include the catalog in the catalog of the library. Now you have like a master library that creates a catalog of all the catalogs. Now you can print the catalog without the catalogs that include themselves. And that super catalog should include that self. But what happens, there's one catalog you cannot print. You cannot print the catalog of all the catalogs that don't include themselves, because once you include it, it should not be there. And if you remove it, it's not in that catalog. So that's why they developed type theory, because instead of using sets to classify elements, we use types. And also, with types, we can make lambda calculus do more controllable things. This, I think we saw this yesterday. This is the omega combinator. This term in lambda calculus never reduced. Once you apply this to this, you end with the same thing. When you apply again, you end with the same thing. So the way to get out of this is to add types. So the one, Haskell Curry developed the type lambda calculus. The terms are the same of the lambda calculus. You have variables, abstraction, application, and constants to make it more usable. And then you have types that is a single type or a function type. And you have like types from constants. So this will get us closer to what we are using now. This is basically just the two main rules of deciding of typing in lambda calculus, in the type of lambda calculus. If you have the type of one term is A to B, and the type of the other term is A. Basically, the application of that gives you type B. And if you have a term of type B and abstraction of type A, basically the abstraction of that, you give a function A to B. It's very simple, nothing really new. But then there's another step. And this is newer. They took the type lambda calculus and they added polymorphism. Now, your types can vary too. And this is like a capital lambda, and this is represent an abstraction of the type. What that means is, here you can see the type is like for all alpha implies alpha, and this is the type of this function. And this is like the polymorphism we know. This one is called system F. And first was discovered by Girard. We're trying to doing like second order logic. And then was discovered again independently for Reynolds that they want to have like polymorphic functions. And really, system F is the base of ML and family and Haskell. Even Haskell, I think it's a flag. They can show you the intermediate language, and it's almost all system F. It replaces all your functions and constructions with applications of for all. That's interesting to see. And the thing is all these things that were like created for abstract reasons, trying to get a complete picture of mathematics, we are using almost straightforward to program. But there's something more even. We already have system F. We are really close to Haskell and ML. We can program with that. We can use it. That's probably the level we are now. But let's take another look. This is very simple code. You have one value of the type A, a function from A to B, and if you apply that, you get a B. Nothing mysterious. If you look at that value level, imagine like we don't have that types. It's very easy. We have an A, a function from A to B, we have a value of B. But if we look at from the types only, we have an A, or type A, we have a function that's A to B, and it gets a B. And that's actually, I just need to put a line here, and it's kind of the simple modus ponens, right? I have a B, and A implies I have an A implies B, that means I have a B. Based on that, it shows that there is some similarities between typing and logic, and people started to explore that. And basically, the work of Howard with the work of Corey, they find out the Corey-Howard equivalence that first it looked like something, okay, they look the same, and they started to move forward, and they found more and more things that they are looking the same. So it points to like a fundamental relationship between types and logic. And it's kind of, for one side, it's amazing, because but if you look at all your programs, you turn it around, you can see it like a proof. But also, based on the history of all this, it's not really that amazing. I mean, we are really using things that were on the fringe of formal logic, and we use that to program. So, expanding that, we have universal quantification that corresponds to generalized product type. I mean, basically it's for all. We have the existence. Implication is a function type. A conjunction is basically a product type, a tuple. Disjunction is a sum type. A true formula is the unit type, and a false formula is the bottom type. And based on that, with this, we can get this. So we can work on logic while programming. And I think that idea, the kind of the equivalence of logic and typing, is really, really powerful. From that, we get theorem programs. We got dependent types. One of the examples, yesterday we saw an example with dependent types. I know also Cog, that is one of the really kind of most powerful tools to work on this level. It's based on the calculus of constructions. It's not exactly Gary Howard, but it's really, really close. But you can mix program code with proofs, and even you write your proof, and you can extract the whole code from your proof. But actually, there's more. And this is kind of, for me, was relatively new. There's another side of the Curry-Howard equivalence. That is, there's a category that also is equivalent to all this. That leads me to category theory. In functional programming, we kind of love category theory because there is a lot of things we can extract and apply. So again, another thing, McLean and Ehrenberg created category theory, but they didn't want to create some new tools to programming, or they were not even working on logic. They were working on natural transformations and algebra, probably close to geometry. They wanted to study natural transformations. To formalize those, they need functors, because a natural transformation goes from functors to functors. And to define functors, they need categories. So there's some kind of, not an accident, but something for them was secondary. And for us, it turned out that that's really, really useful. As a very quick overview, category theory is things and connections. And we only have identity and composition. So it's very, very abstract. That's why they call it abstract nonsense. But one of the most powerful things is this, is composition. One of the most important tools we have, especially when working on functional programming, is composition. How to compose things, how to compose functions. We know the types compose. But with category theory, we have even more constructions to compose and justifications to use them. So anyway, what category theory gave us? I created kind of a small club. We have functors. Functors are really kind of the base of a lot of our work here. All the kind of generalizations of faults and unfaults are all the morphism. Monads, all whatever is co, that is the complementary category, that products, coproducts, all the free structures come from category theory, natural transformations that move from functors to functors. That is, the good thing about type theory and logic are hidden in the compiler, but category theory, we kind of write it ourselves in the code, and this is the most visible part. And as an example, let's say we have this very, very simple program that takes a string, parsed to an int, divides by 2, and creates a new type for that. Why this is helpful? We have our program, we have our future, we want to execute this kind of asynchronously, and we know that future is a functor. So basically, we apply the functor the functor maps one category to another. So we have, basically, we preserve the structure. That's the important thing of a functor. And now our program runs in futures. And we keep the same program. But instead of future, we want option. We can do the same. We just need another functor for option. And we kept the same structure. Even if we have a natural transformation, we can go from options to futures. And again, this is there is an explanation from Bob Harper that they try to create some kind of idea of that logic, programming, and categories are kind of the same view. I mean, there are different views of kind of the same thing. That the combination of all these forms the whole like computation. And yeah, it's called. It's mostly kind of a joke, but it has its importance as how the combination of categories, language, and logic get all together and creates a really, really powerful tool to solve problems. So, is programming math? What do you think? I don't know. People argue that yes, people argue that not, people get really angry. I'm not sure if it's really math, but it's really, really, really close. It's more like a abstract formal logic applied, because really we are, even if we try to ignore, we are like based on all this work. But if we recognize it and go to the core, we can get really good ideas to apply. So, well, I think, yeah, that's what I have. Hope you like it. It was fun.